Let's start.
So subject I'm cover really briefly is how we compute heating and molecular dynamics. Um, so basically, when we heat up a molecule, it requires the nucleus, nuclei, and all these forces interacting with each other. So here are the two equations. The top equation is for the heating, and the bottom equation is for molecular dynamics. Uh, so there's a. This is just the in car for the heating. The important ones is the temperature that you begin at, the temperature that you end at. Uh, so this just relates on how you know your material would react to in real life um, situations. So yeah, if you put the final temperature up to about like 5,000, you should know that your material will probably combust. And so if you do see the molecular dynamics, you just see everything blow up. So this is just important how if you want to control it, the temperature. The other thing that's also important is the end block. So what the end block does is when you introduce a heat to a material, it will cool off after a while, just like anything will in real life. But however many steps you put in it, it's gonna kick it back up to the initial heat or the final temperature that you want it at. So it's just gonna keep kicking it back to that initial temperature. And what that kind of looks like in a face off of a graph is just like this. So you see that the material is decreasing, and then since the end block was 4, it was kicked back up to the initial temperature, then it cools off for a little bit, and just keeps doing that. Since the end block was at 4, you see that every 4th step it is reintroduced to be kicked up. So this is important because whenever you heat it up, the next step is molecular dynamics. So this is just an example of the in-card for molecular dynamics. Uh, so if you haven't seen it before, you just need one of these. And then after that, uh, using VMD, you can also see visually, upload it to YouTube, so you can use it for slides as we have been doing it previously. So yeah, if you follow these settings in VMD, you should be allowed. You can also see the output, so if you have a preferred output, you can. The only thing I wouldn't recommend is just the JPEG frames. Unless you've set it to a directory, it's just gonna give you a bunch of pictures. Just make sure you don't put it like on your desktop or something, because it's just gonna be spammed with images at every step. Yeah. Is there any questions?
Okay, let's continue.
Can you explain what M block is again?
So changing that parameter, it just reintroduces the heat at what you want it to. So since in the previous slide you saw the M block was set at 4, so you see right there. I don't know if you can see it, but 4, it's kicked back up. The material's decreasing until the 4th time step. Then it's kicked back up to the temperature. Then it relaxes down to a stable point. Then at step number 8, it's reintroduced back up to the heat. Then you see step number 12 again, and that's what changing the end block does.
So it means that every 4 steps you reheat it back up again?
Yeah.
Okay.
Any other questions or comments,
How,
concerns?
how long should you repeat this heating if you have unlimited resources?
Well, if you put the end block at
Not in block, but in SW on your slide 3.
oh, the number of cycles.
Mm-hmm.
If you have the well, I mean, you optimize the structure first, but I guess like I would say somewhere around less than 300. You wouldn't want it that much.
Yes, numerically yes, but is there a physical criterion based on this figure? Like if you do it long enough, how this temperature versus time should look?
I think from what this is looking like, it's gotten stable right here. It looks like it's just repeating the same trend.
So it should converge to your desired temperature. It should stop dropping to zero.
Oh, so you're saying it's just gonna stay linear at the top?
It should, yes, it should converge.
Okay. I didn't know that.
More questions to Daniel? If no, let's thank him again.